Okay, good morning. And
Good morning, sir.
we had started with the problems on stresses and strains. So we went through the problems on elongation of the bars. Okay, let us continue with these problems over here. And the first problem we'll take up today is something like this. The following data refers to a mild steel specimen tested in a laboratory. I'll give this data. And we need to determine these quantities. First is the data is here, diameter of the specimen. Mute yourself. So the diameter of the specimen is 25 mm. And the second one, length of the specimen, it is 300 mm. And extension under a load of 15 kilonewton. So extension measured under a load of 15 kilonewton is 0.045 mm. And load at the yield point. Just a minute. So load at the yield point load at yield point is 127.65 kilonewtons. Further, the maximum load is 208.60 kilonewtons. And length of specimen after failure. So that was found to be 335 mm. And neck diameter it is 17.75 mm here. So these are the test details. You have to determine. So determine one is modulus of elasticity. You have to determine Young's modulus and yield point. Then ultimate stress. and percentage reduction in area. Next is safe stress, adopting a factor of safety of 2. So these are the things what you need to determine from the test data. So we have the test data. First thing is we need to know what is the initial or original area of the specimen here. Okay. So area of the specimen, let's say it is A naught initial area. So that comes out to be, since it is a circular specimen, diameter is specified pi by 4 d square. So it will be pi by 4 into the diameter, what is given here, 25 mm. So how much this area comes out? E naught. That area, first of all,
490.87.
490.87. So this area is 490.87 mm square here. Okay, so one is this area. Now what is the stress at the load of 15 kilonewton? There is an extension measured at a load of 15 kilonewton here. Okay, so what stress we come across at that particular load? So stress at load of 15 kilonewton. Okay, so this will be 15 divided by the area what we have calculated now. Okay, 15 into 10 raised to 3, we'll take it in newtons, divided by 490.87. So how much is this stress? 490.87, yes.
Sir, 30.5.
30.56. 30.56.
Okay, 30.56 Newton per
5, 6
mm square. Okay,
mm
so this
square.
is the load stress within the proportionality range. Okay, for 15 kilonewton they have mentioned this. Okay, so still we have not reached the yield point. Okay, so load at yield point is 127. So this is well within that yield point. That is, we are in the proportionality range. So this stress can be used to obtain what is the Young's modulus. For that, what we require is what is the our strain also, because Young's modulus is the ratio of stress to strain. So what we'll do is we'll calculate strain at this point. We are also given with the extension under a load of 15 kilonewton is set here. Okay, so what is the strain here? Strain at a load of 15 kilonewton. We are actually given with the extension at the load of 15 kilonewton. So what you have here, this delta L elongation at a load of 15 kilonewton is 0.045 mm. Okay, so if I use strain relation, that is change in length divided by the original length, I'll be able to calculate this one. So this is 0.045 divided by the length of the specimen. It was 300 mm. So now I have the strain also. So this will be,
So
yes,
1.5 into 10 raised to minus 4.
okay. 1.5 into 10 raised to
0.
minus. Okay, that will be 0.15 into 10 raised to minus 3 strain. Okay, so modulus of elasticity Modulus of elasticity. This has to be determined only within the proportionality limit, because Hooke's law is valid only within the limit of proportionality. So within that limit of proportionality, I can say E is equal to stress by strain. Young's modulus E is equal to stress by strain. Okay, so we have the stress and strain at one particular point of load. At 15 kilonewton, we determined what is the stress here, and also we are given with what is the extension at the load of 15 kilonewton. So now I can apply this for that load. So E comes out to be how much? This 330.56 divided by 0.15 into 10 raised to 3 here. So this will be the Young's
So
modulus for
minus
that
3
material.
no, sir. So minus 3 no.
So minus 3.
Minus 10 raised to minus 3.
So answer is 203,733.33.
So
Okay.
203.73 into 10 raised to 3.
Okay.
203.73
Point
into 10 raised to 3.
into 10 raised to 3.
73
Okay.
into 10
This
raised to 3.
is that okay? Newton per mm square. That is the modulus of elasticity. So this is the first quantity what we determined. Next, what is asked here? Yield point. Okay. So what is the yield point where actually yielding is taking place? So how do we notice the yield point in actual test? We are given with the test data right now, but if you actually conduct this test, how you are going to take this yield point? Now we are provided with load at yield point. Okay, this is how much? 127.65. So many kilometers. So what happens actually is there'll be load which will remain constant or which will not vary much when you are actually testing the specimen. Okay, but extension will be taking place over there. Okay, so that particular point will be initiation of the your yielding. So that is this load what is given to us. If you collect the data when you are testing the specimen, you will come across the certain points where load will not increase too much, but extension will be taking place. So you have to identify like that. Wherever that point of yielding stops, extension will keep on increasing under constant load. Okay, you can treat that load to be constant. There will not be much change in the load. So that is the load what you have to take. That will be our load at yield point. So right now we are given with this one. So this is the load at yield point. What will be the stress at the yield point or the yield stress? So it will be this load divided by the area. Okay, we can call it as sigma y 127.67 into 10
It is
raised to
65
3.
not 67 sir.
Yes,
So 127.65
6.5
given.
is there given. Yes,
Yes sir.
6.5. Okay, 6.5. So 127.65. Right. So calculate this one. 127.65 into 10 raised to 3 divided by 4. What was the area? 490.87. 87 mm square. So this will be our yield stress here. 127.65.
So
So
260.04.
260.04 mm.
260.04 Newton per mm square, right? So 260.04 Newton per mm square. That is the yield stress. Now, next quantity what we require here is what is the, so what is that? Percentage elongation. So once the test is done, what is the percentage elongation that you need to find out? So final length minus initial length divided by the original length or the initial length into 100. That will tell you the percentage elongation here. So next is percentage elongation. So this will be equal to final length minus initial length divided by initial length. It is in terms of percentage, so into 100. So what we have, final length as 375 mm minus 300, okay, divided by 300 into 100. So how much this comes percentage elongation?
So 25.
So this will be 25%. Okay, this is percentage elongation. Keep that in mind. This is not the strain what we have measured. Strain is actually measured on a gauge length or a small length. Here we are expressing the percentage elongation. This is done only after the test. What is the percentage elongation? And percentage reduction in the area. So this comes out to be initial area minus the final area divided by the initial area. Okay, now after the test you will find that there is a reduction in the diameter of the specimen, so it will be initial minus final. Okay, whereas this elongation, when it is asked about elongation, final minus initial, okay, divided by the initial length. Here reduction in the area, so initial minus final divided by the original area or the initial area. If you want it in percentage, into 100, or this simply what you can do is pi by 4 into, say, if you have the final initial area as d naught, okay, minus pi by 4 into let's say d1 square divided by pi by 4 into d naught square, or simply you can put it as initial diameter is a square of initial diameter minus the final diameter square divided by initial diameter square. I can put it percentage elongation in this form. So I have to just consider the diameters, that's all. So initial diameter was 25 square minus final diameter, what is there, 17.75 square divided by 25 square. So this will be the percentage reduction in the area.
So 49.59.
49.59. So this will be 49.59%. This is the reduction in the area. The area has almost reduced by 50%, 49.59%. Okay, that is a reduction in the area. Now, next, what we require is safe stress, adopting a factor of safety of 2. Okay, so for that we'll go for calculating what is the ultimate stress. Okay, what is the specimen given to us, mild strain, so it will be yield stress. Okay, so it will be yield stress upon factor of safety here. I think we need to calculate ultimate stress. We have calculated here. Okay, we have to calculate ultimate stress. Fine. Let us calculate this. So yield stress was somewhere 200. Okay, 260.04. So this will be 260.04 divided by 2. So this safe stress comes out to be 130.02.
Yes, sir.
130.02 Newton per mm square. Okay, so you can express this safe stress in two ways. One is ultimate stress by factor of safety, or yield stress by factor of safety. If the material is ductile, it will be yield stress by factor of safety. If at all, if you have the brittle material, then it will be ultimate stress by factor of safety. Okay, because we don't find clear yield point in case of brittle materials. Okay, and ultimate stress So what will be the ultimate stress here? Maximum load divided by the cross-sectional area. So what we have maximum load as 208.6 in that problem, 208.60 into 10 raised to 3 divided by cross-sectional area 490.87. So 208.6 divided by 490.87.
So 424.95.
Okay, this is sigma u, you can say 420 point 420 point, what is that?
So 424.95.
4.95 Newton per mm square here. Okay, that is the ultimate stress. So these are the test results and what are the calculations we'll get from the test. Okay, then is that fine? If at all, if you have the test results, this is how you can obtain the quantities what are asked.
Excuse me, sir. Sir, please
Hmm.
show the question.
Which one?
The sum
This
which solved. Sir, now just
one.
now which. Okay, sir. Thank you.
Okay, just a minute. Okay, one more question from this question for what I have here. Mm, one sec. Okay, for the bar shown, in the figure, find the stresses in the three parts. Find the stress in the three parts and the total extension. The total deformation for an axial pull of 40 kilonewtons. Take E as 2 into 10 raised to 5 Newton per mm square. Okay, so this is the problem. I'll give you that bar. bar is something like this. We have 3 sections in this one. This is one section. Okay. And the next section is over here. Okay. And one more part of this bar is on this end. Okay, so the load what is applied is 40 kilonewtons axial load. This is the axial load, and on this end okay, this is the bar. And the length and diameter of different sections are first section the length is 180 mm. So for this the length is 180, and the middle section is of length 260 mm, whereas this last portion is of length 160 mm. And diameters, okay, so this is of 20 mm in diameter, and here the diameter is 32.5 mm, and then over here the first section it is of 30 mm diameter. Okay, so loads are 40 kilonewton. This is also 40 kilonewton. Okay, you need to find what are the stresses in each of these segments. Okay, so yesterday we have taken a bar with the uniform cross section, such same simple bar, but this is a bar wherein the cross section is varying. So we'll find the total deformation. Okay. So I given the diameter, this was 30, and here diameter is 20. Calculate these areas if you have those diameter with you. 180 mm in length. This is 260 mm, and this was 160 mm. Diameter 32.5. All are in mm. 40, and this also 40. So first area, for the first section, what is the area? Let us proceed with calculating the deformation and stresses as well, so that we can finish off each area when we take up that. So in the first area, first section. Okay.
So first one is 706.85 mm square.
It is area.
Yes, sir.
Okay. I'll call them as this is 1, 2, and this is third section. Okay. And then for first section or first portion, A1 5 by 4 into 30 square. So this comes out to be
706.85.
706.85 mm square. Okay. So what is the load in this section? So yesterday we did a calculation for determining the load here. Okay, so in this case there are no intermediate loads which are applied over here. Okay, so entire bar will be subjected to a load of 40 kilonewton. All these portions will be experiencing a load of 40 kilonewton only. So there will not be any load differing from one section to another section. So the first section will be having a load of 40 kilonewton. In the middle section also the load will be 40 kilonewton, and in third portion also the load will be 40 kilonewton only. Okay, so it will not change with one section to other section because there are no loads which are applied in between. Okay, so in this stress, that is the sigma 1, we can take it. So every time the stress will be load upon the cross sectional area. So here it is 40 into 10 raised to 3 divided by 706.85. So sigma 1
56.58.
56.58.
6.58. Similarly, what will be the elongation? So 56.58, 56.58 Newton per mm square. Okay, then in this elongation of the section, that is d1, dl1 or delta l1, you can say it will be pl by ae. Okay, the respective length area has to be substituted here. So P is 40 into 10 raised to 3. Length was 180. Area is 706.85. So here the length is 180 mm divided by 706 point, was that 85. 85 into 2 into 10 raised to 5 Newton per mm square, Young's modulus E. So this will be the deformation in the first segment.
Sir, 0.051.
51 mm. Okay.
mm.
So here the second segment, we can take A2, which will be pi by 4 into 20 square.
Sir,
Okay.
314.15 answer.
Area
Yes, sir.
A2. Okay. So this will
And
be,
stress is 127.32.
just a minute, 314 point,
15.
okay, 15 mm square. I have L2 as 260 mm. So stress in the second portion will be 40
127.32.
3, okay, 314.15. So this is 120 point
127.32.
127.32. 127.32 Newton per mm square. Okay, and elongation of the second segment, that is DL2 or delta L2, it will be PL by E. Okay, so that will be 40 into 10 raised to 3 into 260 divided by 314.15 into 2 into 10 raised to 5. This is elongation or extension in the second segment. Okay, and
0.165.
0.165 mm. Okay, and taking the last segment, what we have for that, 32.5 is the diameter over there, and length, okay, third segment, the area
Sir,
will be, yes,
829.15.
area
Yes, sir.
329.15
Sir,
mm,
829.
829, and L3 is 160 mm. Others, if you have any difficulties, please unmute and ask if you are not following this. And now what we require is what is the stress? Sigma 3. What is the stress here? So that will be 40 load into 10 raised to 3 divided by 829.15.
Sir, 48.24.
0.24 Newton per mm square. And the elongation of the third section. So again, we have this PL by E delta, or it will come out to 40 into 10 raised to 3 into 160 divided by 829.15 into 10 raised, sorry, this is what that comes out, the elongation.
Sir, 0.038.
0.038. Okay, I don't have that next part. It is gone. Okay, that will be the elongation of third part. And what about the total elongation? We are asked to determine total elongation. So what you have to do is add up all the three elongation: delta L1 plus delta L2 plus delta L3, or our extension. There is an elongation. Okay, so you have to add up. There is nothing that the compression is coming in some part. So it will be the total elongation will be elongation of first part plus second plus third. Okay. Yes.
Sir, 0.254.
Okay, that is a total elongation.
0.0254 mm.
Okay. So further, mm, a brass bar, is that okay? Any difficulty in that part in this particular problem? I hope you are able to
No,
calculate the
sir.
stress and elongation.
Yes, sir.
Okay. Others, I don't know if you have any doubts. Please ask. You have to unmute and ask yourself. Ask me about your doubts. Okay. Now, next one. A member ABCD is subjected to point loads point loads P1, P2, P3, and P4 and P4 as shown. Calculate the force P3, the force P3 which is necessary for equilibrium. Given P1 is 120 kilonewton, P2 is 220 kilonewton, and P4 is 160 kilonewton. Also determine the net change in the length. Net change in the length if E is equal to 2 into 10 raised to 5 Newton per mm square. This is the Young's modulus or modulus of elasticity of the steel, what we are coming across, 2 into 10 raised to 5 Newton per mm square here. Okay, in most of our problem we have come across that. But for different materials, E will keep on changing. So the bar what you have here is okay. So to this, two more bars or segments are attached over here. So on this right side, okay. So on this, what you have is the forces which are applied are so you have four forces coming over here: P1, P2, P3, and P4. Out of which P1, P2, and P4 are told to us, and we need to first determine what is P3, then go for calculating the extension of the member over here. So where are these P1, P2? This is P1, okay, and over here is P2. These are all axial loads, and this is P3, and at this end you have P4 here, okay. And what are the cross section? This is first segment. It is of 40 mm by 40 mm here, okay. This middle one is of 25 by 25 mm in cross section, and the last segment is of 30 by 30 mm in cross section. They are all square sections. By dimension we can make out that the lengths here are 0.75 meters. This first one. The second is of 1 meter in length, and the third segment length is 1.2 meter. Okay, this is not to scale, just leave that part. So this is the length of each segment. Okay, so first is what is this load you have to calculate before we go for determining the entire this one elongation. You need to find out what is this P3. How do you get that P3 value?
Sir, first we have to convert this into mm na sir.
Okay, your dimensions will convert them. We are not yet come to the calculation of deformation because one of the load is not given to us. So P3 is not given here. This P3, what is applied, that has been asked. It is not given to us. So let us first find out that P3, then we'll go for calculating the deformations. There you have to convert them. You have to convert this length to mm. You have to take it in mm. So what should be the value of P3? P1, P2, and P4 are given to us. Okay. Any idea for that? Yes. P3, it has to
Sir,
be
PL by A. Sir,
PL
PL
by
by A by section.
okay, you'll do that. Then
By that we can find the P3.
by that, how you are going to find P3? You'll find the deformation of first segment, second segment, third segment. Okay, you'll get them. Okay, but
Yes, sir.
in that
Then
P3
only
is not known.
P3.
P3 is not known to us.
Sir, in third section.
We can, sir.
Third
Yesterday,
section.
What is that?
Calculation.
What
sir,
calculation?
yesterday I asked, sir. Yesterday I asked that the starting and end point, whichever the load is given, we have to take same elongation. That one, so
Yes.
160 we have to
Uh,
take, sir.
okay. Uh,
Yeah, P3 160.
P3K may not be 160. Okay, you have to calculate that. What we have is it should be in the static equilibrium. This entire bar should be in static equilibrium. Okay, so what we can do is we can use the condition of equilibrium here. For equilibrium. Okay, so first is we have to make sure what is P3. How you are going to find out P3 is apply the condition of equilibrium. These all forces are collinear forces. So what condition of equilibrium is valid is you have it has to satisfy summation fx should be 0. Okay, this condition can be used for determining what is P3 here. So what should happen if you consider the sum P1 plus P2 plus P3 plus P4 is equal to 0. That should be considered here. So that will tell you what is P3 actually. Okay, you can take this last segment and you can check it. Okay, but it should also be in equilibrium. That is also a necessary condition what we have here. So if you take this condition of equilibrium, what we have P1 is 120, but it is acting towards left. So minus 120 sign convention. That is what we are going to do is P2 is 220 and it is acting in the right direction towards right. So plus 220. Okay, this P3 I don't know. Okay, it is shown that it is acting towards left, so minus P3. P3 is not known to us. Okay, and finally plus P4. What is the value of P4? 160. 160 should be equal to 0, or this will tell you what is this value of P3. How much should be P3 here? So how much it comes out?
0.
Yes, no. P3, calculate this.
So 260.
So P3 comes out to be 260 kilonewtons. Okay, 260 kilonewtons. Okay, so this is 260 P3 actually. Now we can go segment by segment. If you take the first segment, see what force will be acting here.
Excuse me, sir. It will come
Yes,
in minus sign, no, sir.
we
Just
have
if
considered that direction already. Minus I have considered here. Okay,
okay, but is equal to 0 is there, so we are shifting that side. It means the minus.
you shift in. I think what happens, what sign it comes, it is minus 260.
Yes, sir.
It is coming here to be
If we are
minus 2.
shifting that side. So minus 120 plus 120. So plus 100 plus 160. So plus 260. So plus
Hmm.
260 shifting that side minus 260. No, sir.
I'll take P3 only this side. Okay. So what
Okay,
it
sir.
gives me P3 will be equal to minus 120
Two-
plus 220 plus 160. What will be this? I think plus 260.
Yes, sir.
Huh? I have
Yes, sir.
shifted P3 on the other side. Directly P3 I can shift it. Then add the sum. It should come out to plus 260.
Sir,
Okay.
even if you keep
Okay,
P3
sir.
that side, if you shift 260 that side, minus 260 and minus P3, minus gets cancelled, sir.
That's what. P3 is coming out to be positive plus 260. Right?
Yes,
Yes,
sir.
P3.
sir.
Yes, sir.
You do it in any way. It doesn't matter. But what is the direction? We have already considered that. Okay, whatever sign it gives, that will be taken. Plus 260 means it is towards left, it is acting towards left. Okay, in the direction what is shown here. If at all if it is coming negative, then it will be in the opposite direction to this. Okay, so I hope in this calculation it will come out to be plus 260. Is that fine?
Yes,
Yes,
sir.
sir.
Okay, now what you have to do is take each segment one by one. First segment, if you take P1 is here, which is of 120 kilonewton. The other side also you should get the force of 120 kilonewton by adding P2, P3, and P4. So that should be the force over here. If still any doubts are there, please ask. Don't worry about that. You can ask any doubt. If it is clear, the next part is as good as solving the yesterday's problem. Okay, what we have dealt with that. So this is the first segment, right? What we have here. So length was 0.75 meter. Okay, so that is 750 mm. We'll take it in mm. 0.75 meters, 750 mm. What is this force? This is P1, which is of 120 kilonewton. The other side also, the force has to come out to 120 kilonewton. If you add up P2, P3, P4, that should result in 120 kilonewton. Check that. Side is 40 by 40 mm. Okay. So earlier we came across circular cross sections, but this time it is of square cross section. The cross section is this.
40 by 40, 1600. So
Okay, 1600 mm. That is the area. What you have to find out here? Elongation. Sorry. So it will elongate since forces applied are tensile in nature. They are acting away from each other. So they are tensile in nature. So what it should come out? So elongation, we should get extension of the bar. Okay, so D1, DL1. Okay, we will be using this PL by E extension of the bar. So what is P? 120 into 10 raised to 3 into 750 is the length for the segment divided by area 1600 mm square. So this area is 1600 mm square cross sectional area into 2 into 10 raised to 5. So what will be this?
so 0.281. 0.281.
0.281 mm. These extensions you take it to the third decimal. Okay, they'll be small, so 0.281. Better you stick to rounding of the third decimal. Okay, not before that. Extension of second segment DL2. Expression will be same for extension. So what I have for that extension. Now in the second segment, we need to go for calculating the forces to which it is subjected. Then we'll come to know whether it is subjected to compressive force or the tensile force. So in this segment, here there is a force of how much? P2. Okay, let me go back over here. P2 and P3. So P2. This is P2. This is P3. 260 kilonewton. What was P2 value? P2 is 220 kilonewton. Yes, 220 kilonewton. Then P1 is there coming on the side, which is of 120 kilonewton. And on the other end, what you have? P4, which is of 160 kilonewton.
160 kilonewton.
Okay. So what is the force on this face? What is the force on this face? 120 minus 120 plus 220. So this should be 100 kilonewton, right? On this face also, you should get a force of 100 kilonewton, equal and opposite to this one. So this middle segment is subjected to a compressive force of 100 kilonewton here. Okay. So that is the force, what you need to determine before you go for determining the extension of this middle segment. Okay, so these are the forces here on this middle segment. Is that clear? Here you need to go for calculating this. What is the net force acting on this segment, and what is the nature of force, whether it is compressive or tensile, that has to be ascertained first. And this length is of 1000 mm, that is 1 meter. What is the size here? It is of 25 by 25. Cross section is of 25 by 25. So this is also a square cross section, 25 by 25. So area will be 25 by 25. 625 mm square.
625.
Okay. So elongation over here will come out to be 100 into 10 raised to 3 into length is 1000 mm, PL by A, 625 mm square into E, 2 into 10 raised to 5. So you'll get to know what is this DL2 here.
Sub 0.8.
0.8. Okay. Yeah. What about the third segment? Third segment will be subjected to a extension of 160 kilonewton. P4 is on one phase, acting on one phase. So on the other phase, the net force should also come out to be equal to P4, but in opposite direction. From that, you will be able to get what is the extension by using the same expression A and L for that particular segment. Okay. Please put your name and USN in the chat box. Okay, please go to this, do the calculation, further calculation. Any doubts regarding the problems what we have taken out till now, you can ask them in the next class when we meet tomorrow. Okay. If you once you are given the attendance, you can exit from the meeting. You can join for next class.